All right, so in this video, we're going to be looking at how to convert between different coordinate systems, but we're going to be dealing with functions instead of points. Now, sometimes you'll see in textbooks that they'll recommend that you use certain identities to do conversions between, let's say, rectangular to cylindrical or rectangular to spherical, but which systems, which expressions actually, which identities actually work the best is going to depend on not only the direction that you're converting in, but also whether you're working with points or functions. And I find that um, because they give directionality sometimes in textbooks, that actually can create problems because when you're going from points to functions, you'll use one set. But when you're going from functions, or so when you're going from working with points from, let's say, rectangular to spherical, you'll use one set of identities. But when you're using functions, you'll actually use the other portion of the identities. So um, sort of ignore the directionality and directions that they give you, like rectangular to spherical or rectangular to cylindrical or what have you, because again, um, it's going to depend on whether you're dealing with functions or points, and that you're going to really use the opposite ones when you're dealing with the two sets. But you should use any of the identities that will get you to your solution with the least amount of algebra possible. I have seen students kind of slave away at doing identities and using x equals r cosine theta and y equals r sine theta, and then of course not simplifying when they have x squared plus y squared. I mean, you really want to make sure that you're doing the identities as efficiently as possible because you do need to simplify. All right, so the other thing to keep in mind is that when you're in rectangular, z is considered the function variable. When you're in cylindrical, z is also considered the function variable. But when you're in spherical, rho is considered the function variable. So when we convert to spherical, we should try. We may not always be able to succeed very nicely, but we should try to solve for rho. All right, so let's see how this goes. So we're going to start with x squared plus y squared equals z. And if we're going to convert to cylindrical, then that's very straightforward because we have the identity x squared plus y squared is equal to r squared. And so our function is just z equals r squared. Boom. Done. Again, don't feel like you have to plug in r cosine theta and r sine theta, because what's going to happen if you do that, you're going to end up with r cosine theta squared and r sine theta squared, which is r squared cosine squared theta plus r squared sine squared theta. And then you have to factor out the r squared cosine squared theta plus sine squared theta, which is equal to 1. And you're back to exactly where you would have been if you had just used x squared plus y squared is equal to r squared directly. So again, you do have to do the simplification. You can't just plug things in and say, whoop, I'm done. And the other thing, of course, to make sure is when we're doing these conversions, that our final answer has only, in this case, r, theta, and z. It might not have all of them, but it can't have any x's or y's or anything else left over. It has to be fully converted into the one coordinate system. So that's our rectangular, our spherical, our cylindrical, sorry, cylindrical conversion. So in cylindrical, x squared plus y squared equals z becomes z equals r squared. Now in spherical, then again, these other identities that sometimes get included in expressions of converting from cylindrical to spherical and sometimes get left out. This is the kind of identity that will be really helpful here. And you can, if you want, convert from directly from cylindrical into spherical since we've done this already. That would be very straightforward. In this case, we would just end up with rho squared sine squared phi is equal to z on the other side would be rho cosine phi. And then we would divide out one of the rows, rho sine squared phi equals cosine phi. And then to solve for rho, we would have rho cosine over sine is going to be cotangent. And then one additional sine would make it cosecant. And that would be our spherical. X squared plus y squared is equal to z becomes this. All right, so now again, you can try to convert directly from rectangular, but if you do that, you will have to do the simplifying. So again, let me just kind of walk through it again, just so that we're clear. X squared would be rho cosine theta sine phi squared, and then rho sine theta sine phi squared is equal to rho cosine phi. Again, you can't leave it like this. So we would end up with rho squared cosine squared theta sine squared phi plus rho squared sine squared theta sine squared phi equals rho cosine phi. But again, we can't leave it like that either. So we take out, what do these two things have in common? Rho squared and sine squared phi. So rho squared sine squared phi. And then we're left behind cosine squared theta plus sine squared theta equals rho cosine phi. Again, I can divide out a row, just leave a row, and sine squared phi. But then cosine squared plus sine squared is 1. And then finally, I can divide my sine squareds over and get rho is equal to cotangent phi cosecant phi. Now again, that's a lot more algebra. You get the same answer, but why do all that extra algebra if you don't have to? Use these identities in the most efficient way that you possibly can. All right, so now let's look at our next one. So we're starting in cylindrical, and we're going to try to convert this to rectangular and spherical. So let's copy our formula. All right, so if we're trying to go to rectangular, what I would recommend is to use an identity on our sine 2 theta. We don't have any identities that involve 2 theta, but we do have ones involving theta. So sine 2 theta is 2 sine theta cosine theta. And so that's going to be 2r squared sine theta cosine theta. And since we have information that involves r sine theta and r cosine theta, I'm going to split this into r sine theta and r cosine theta. And so in rectangular, this will be 2xy. And of course, for rectangular, we don't have to change the z coordinate from cylindrical. Great. So how would we do this transformation in spherical? Well, we're going to need z is rho cosine phi. And then on the other side of the equation, r squared, we're going to use that rho squared sine squared phi identity. And the sine 2 theta, we're going to make this, we have to make the same transformation. I mean, I suppose we could leave it because we're not, we need theta in the original problem. And we have it in spherical, so we could leave that if we wanted, or we could convert it out. Remember, the main thing is we want to get rid of anything that doesn't belong in spherical, which is definitely all the r's. We want to solve for rho in spherical, so we're going to divide everything by rho cosine phi is equal to 1 rho, and then sine squared phi sine 2 theta. And then if we're going to solve for rho, then we're going to have to just move everything over to the other side. Now, cosine phi divided by sine squared phi, we already saw in the previous problem that this was cotangent phi cosecant phi. But then the sine 2 theta will come over as cosecant 2 theta. And so in spherical, E equals r squared sine 2 theta becomes this. Now, let's think about what these shapes might look like. By the way, our original problem in rectangular, this was a paraboloid, a circular paraboloid. That's what that looks like. This is a hyperbolic paraboloid that's been rotated 45 degrees. So that's what that looks like in spherical. I mean, I suppose it could be worse, right? And then let's look at our spherical equation and try to convert this. Now, whenever you see a cosecant like that in a spherical equation, you should try to move it over to the other side of the equation so that you have a sign. So rho, if we multiply by sign on both sides of the equation, we get sine phi is equal to 4. Now, if we don't have any relationships that have just rho sine phi, but we do have rho squared sine squared phi. So I'm going to square everything. Now we know that rho squared sine squared phi is equal to r squared, which means that in cylindrical, r is equal to 4. So this is actually just a cylinder in cylindrical coordinates. And since that was the easiest one to come up with, we'll just do that one first. Our original problem was rho is equal to 4 cosecant phi. And from spherical to cylindrical, we end up with r equals 4. Now, since we know that r squared is equal to rho squared sine phi, we do in principle have the identity that r is equal to rho sine phi, so you could go there directly, but it depends on what formulas you have in your list. Again, sometimes I've seen the r squared equals rho squared sine phi in the cylindrical conversion, but often it's in terms of the square and not the r by itself. But either way, that wasn't too bad. Now, once we have it in cylindrical, then getting it back to rectangular isn't too bad. We're going to start with the r squared equals 16. In rectangular, we know that this is x squared plus y squared is equal to r squared. And so again, we're left with this cylinder rho is equal to 4 cosecant phi becomes x squared plus y squared equals 16, which again is just a circle in the plane. And since z is free, this is a cylinder.